So now let's go on to the next step, which is rather than allow the natural decay process in which we have just a small portion of the nucleus is ejected and we still have a rather large nucleus, we're going to undergo the fission process. The fission process is somewhat similar. We're going to break down the nucleus into smaller parts, but rather than one very large part and then one tiny little particle like an alpha particle or a beta particle, we're going to end up essentially splitting the nucleus into two relatively equal parts with the release of some additional neutrons also. So nuclear fission is somewhat similar, but rather than small pieces, we're actually going to split. We're going to split the nucleus. And the way that we do this is we fire a high-speed neutron into the nucleus. It's essentially like sending a bullet through a brick wall, and the brick wall is going to shatter as a result of it, and we'll end up with two smaller pieces. So this one, what we're going to do is we're going to fire a high-speed neutron So we need to fire a high-speed neutron, and in this case, let's go ahead and break apart the same example they use in the book. We're going to use uranium-235. Uranium-235 is similar, of course, to uranium-238, but it's a little less stable. It actually breaks apart a little bit more easily, and this is the same thing that we use for our first nuclear weapons, and we also use this in our nuclear power plants. It turns out that when we fire these two guys together, for just the briefest of instances, we actually end up creating a slightly more massive version of uranium called uranium-236. But the uranium-236 very quickly breaks down, and the uranium-236 breaks down. Now there are actually a number of possibilities. We're just going to look at one possible example. One of the possible examples when uranium fissions, that is to say breaks apart or splits apart into two atomic nuclei, is that we end up producing barium-144. Barium has an atomic number of 56. We end up producing krypton, which has an atomic number of 36 and a mass of 89. And if you notice the Z numbers, 56 plus 36, that gives me 92. That accounts for all of the protons. Now if I add up the A number, 144 plus 89 gives me 233. So I'm actually missing no protons are missing, but I am missing 3 neutrons, and that's because this reaction releases 3 neutrons. So we started with one high-speed neutron. As a result of the fission process, we actually ended up with 3 more neutrons. Now these 3 neutrons could very easily go on to hit another nucleus of uranium-235. In fact, I could hit 3 nuclei now. Those 3 nuclei would split. They would also produce the 3 neutrons. So now I have 9 neutrons. Those 9 neutrons could go out and hit 9 different uranium-235. As each of those fissions, I would produce 3 more. That would give me 27 neutrons. Then you can see that ultimately what we end up doing is we create a chain reaction. And we're going to look at that chain reaction in just a moment. But first, let's see what kind of energy we're able to release from this particular reaction. So what we're ultimately doing is going from this, the 1 neutron plus the uranium-235, to produce barium, krypton, and the 3 neutrons over here. So let's rewrite the reaction, and we're going to skip the 236 portion right here. So that is 1 neutron plus 235, 92 uranium, and that is going to go on to produce 144, 56 barium, plus 89, 36 krypton, and of course plus our 3 neutrons. Okay, so you know the atomic mass, the nuclear mass of 1 neutron is 1.08665. Plus we need the atomic mass of uranium, so we'll look that up really quickly in the back of the book. And turns out uranium-235 has an atomic mass of 235.043925. Those guys will produce. Now, one thing just to remind you very quickly, we have to follow that basic principle. The basic principle is that the parents have to have more mass than the products. And as a result of having more mass on the left side than I have on the right side, that missing mass, which is of course known as the mass defect, is going to be transmutated, I should say, into the energy, the binding energy that's going to be lost. And we're going to end up releasing energy. The left side has to have more mass than the right side. That's the basic principle of nuclear reactions. So the barium-144 turns out to have a mass of 144 point, sorry, I misspoke, 143. 143.92292. The atomic mass of krypton is 88.91781, and then we need to add 3, we'll put that in parentheses, 3 neutrons. That's going to be 1.08665. Of course, these are all in terms of atomic mass units. These are all U's, each one of these guys. Okay, so if we add these up, we have 1.08665 plus 235.043925. That gives 236.05259. And let's see what we get on the other side. On the other side, we have 143.92292 plus 88.91781 plus 3 times 1.008665. And that gives us 235.8666725. Very clearly, we've satisfied that basic condition that our products on the right have to have less mass than what we originally started with. And as a result of that, what we have in addition to the mass and the particles that we have on this side is we also have some energy, some missing energy. Where is that energy going to go? It's going to go into the kinetic energy of the 5 particles, the 2 atomic nuclei plus the 3 neutrons. Each of these guys will travel away at a very high speed, particularly the neutrons because they're so small, and the energy is going to be released then in the form of kinetic energy. So let's take a look at the mass defect. That's going to be the 236.05259 minus 235.8666725. So 236.05259 minus 235.8666725. That gives me a mass defect of 0.18585, and that's U's. Now we can use the conversion to convert this mass into energy, because we realize that starting with the 0.18585 U's, and we know that 1 U is equal to 931.5 MeVs. So if I multiply that by 931.5, I end up with 173.1 MeVs. So for each nuclear uranium atom, 235, that I split, I'll end up with 173.1 MeVs. Now let's go ahead and think very quickly, just do a real quick calculation. What if I had the same amount of mass that I had in the previous problem? Let's say that I had 50 grams of uranium-235. How much energy would I be able to produce? So in the book they use 1 kilogram, but in our case, let's use as our example 50 grams of uranium, sorry, no mistake, So how much energy can we produce with 50 grams of uranium-235 through the fission process, not through the natural decay process? Uranium-235 does undergo the natural decay process. It goes through a series of alpha and beta decays. Occasionally there'll be a gamma decay in there. But if we split the thing in half, then we actually will end up with, we'll get much more energy. If you remember, we got 4.84 MeVs from the decay process of radium, for example. So we're able to get quite a bit more energy. So let's start by, first of all, figuring out how many atoms of uranium-235 that I have. If you remember, I have 50 grams, and this 235 means that there are 235 grams in 1 mole, and in 1 mole there are 6.022 times 10 to the 23rd atoms. So let's go ahead and figure out how many atoms we have. That's 50 times 6.022 to the 23rd divided by 235. So that gives me approximately 1.28 times 10 to the 23rd atoms of uranium-235. Now, if I multiply these two numbers together, that would tell me the total amount of energy I'll release if I cause the fission of all of those atoms. So let's go ahead and calculate that by multiplying by 173.1, and I end up with approximately 2.217, let's say 9 times 10 to the 25th MeVs. Okay, and let's go ahead and make a quick conversion of that into joules, because I know that in 1 MeV there are 10 to the 6th EVs, and I know that in 1 EV there is 1.6 times 10 to the minus 19th joules. And so, making this calculation then, I end up with approximately 3.55 times 10 to the 12th joules. That's a very large amount of energy. So remember, if we were to use that 100 watt light bulb as our example again, then I would divide that number by 100. This would give me the number of seconds that I'll be able to operate that light bulb using this much energy. So let's divide that by 3600. Let's divide that by 24 hours in a day, and let's divide that by 365. So a 100 watt bulb could run for 1,125 years on that much energy. And again, to remind you, that was using only 50 grams of uranium-235. I could operate a 100 watt light bulb for more than a millennium.